A subtle gravitational wave hum from merging black holes may help settle the cosmic fight over how fast the universe is expanding. Astronomers have understood for many decades that the universe is expanding. To calculate how quickly it is stretching today, researchers measure a value called the Hubble constant. Different techniques are used to determine this number, and because they rely on the same underlying physical laws, they should agree. Instead, measurements based on observations of the early universe do not match those based on the more recent universe. This discrepancy is known as the Hubble tension, and it remains one of the most important unanswered questions in cosmology. A team of astrophysicists and cosmologists from the Granger College of Engineering at the University of Illinois Urbana-Champaign and the University of Chicago has now introduced a new way to estimate the Hubble constant using gravitational waves, which are tiny ripples in space-time. Their approach improves the precision of earlier gravitational wave techniques. As detectors become more sensitive in the coming years, this strategy could lead to even tighter measurements and help clarify the source of the Hubble tension. This result is very significant. It's important to obtain an independent measurement of the Hubble constant to resolve the current Hubble tension. This method is an innovative way to enhance the accuracy of Hubble constant inferences using gravitational waves. It's not every day that you come up with an entirely new tool for cosmology. Researchers showed that by using the background gravitational wave hum from merging black holes in distant galaxies, we can learn about the age and composition of the universe. This is an exciting and completely new direction, and we look forward to applying these methods to future datasets to help constrain the Hubble constant as well as other key cosmological quantities. Since the early 20th century, efforts to measure the universe's expansion have followed two main paths: methods based on electromagnetic observations and methods based on gravitational waves. One widely used electromagnetic approach relies on standard candles, such as supernovae, which are bright stellar explosions. Because scientists understand how luminous these explosions truly are, they can determine both their distance from Earth and how quickly they are moving away. Together, those measurements reveal the expansion rate of the universe. The discovery of gravitational waves opened a second route. These waves are produced when extremely dense objects, including black holes, collide. The ripples spread outward at the speed of light, similar to waves moving across water after a stone is dropped in. On Earth, the LIGO-Virgo-Kagra LVK collaboration, a global effort with more than 2,000 members, operates the instruments that detect these signals. Gravitational waves can also provide distance measurements through what is known as the standard siren method. However, determining how fast the source is receding due to cosmic expansion is more challenging. To measure that motion, astronomers usually need to detect light from the merger or identify the galaxy where it occurred. If all techniques were perfectly aligned, they would produce the same Hubble constant. The fact that they do not suggests something may be missing from current models. Possible explanations include early dark energy, a proposed influence that would have altered the expansion rate in the young universe. Interactions between dark matter, which makes up most of the universe's matter, and neutrinos, or changes in how dark energy evolves over time. In the new research, researchers proposed a different strategy. Instead of focusing only on black hole mergers that detectors can clearly identify, they analyzed the combined signal from many distant collisions that are too faint to be individually observed. Together, these unresolved events form what is called the gravitational wave background. The researchers show that if the Hubble constant were smaller, the observable universe would encompass less total volume. In that case, black hole mergers would be packed into a smaller region of space, increasing the overall strength of the gravitational wave background. If that stronger background is not detected, it effectively rules out slower expansion rates. They refer to this approach as the stochastic siren method, reflecting the random nature of the mergers that contribute to the background signal. Using existing LVK data, the team demonstrated that even without directly detecting the gravitational wave background, they could place limits on very slow expansion scenarios. When they combined this method with measurements from individual black hole mergers, they achieved a more precise estimate of the Hubble constant. The resulting value lies within the region associated with the Hubble tension, showing that the method can meaningfully refine cosmological measurements. As gravitational wave observatories continue to improve, this technique is expected to become more powerful. Scientists anticipate that the gravitational wave background could be detected within about 6 years. Until then, increasingly strict upper limits on the background signal will continue narrowing the range of possible Hubble constant values. This should pave the way for applying this method in the future as we continue to increase the sensitivity, better constrain the gravitational wave background, and maybe even detect it. By including that information, we expect to get better cosmological results and be closer to resolving the Hubble tension. Thank you for watching. If you've enjoyed our videos, subscribe to our channel for there's more to come.